My name is Rich Nuccitelli. I'm Chief Science Officer for Pulse Biosciences. I'd like to explain today what is unique about the pulses that we use for Nano-Pulse Electro-Signaling. The pulses we use for Nano-Pulse Electro-Signaling has three unique features. The first is that they're very short. Now, they're 100 nanoseconds or so. It's hard to imagine how short this is, but if you put all of these pulses together right next to each other, you could fit 10 million in 1 second. So that gives you some idea of how short. They're also very large, thousands of volts. Now you might think, how can we put thousands of volts on cells without damaging the cells? The trick is that the thousands of volts are only applied for this very short 100 nanoseconds. That means the packet of energy is very teeny and so small that it doesn't even heat the cell. And then finally, these two features allow the cell pulses to penetrate the cell interior, and this allows them to act on intracellular organelles. So when a cell is put in an electric field, the interior of the cell is a conductor. So it means that the ions are free to move until there's no force on them. So let's say you have positive and negative ions in the cell, chloride, potassium ions, sodium ions. You put them in a field and the negative ions are attracted to the positive pole. The positive ions are attracted to the negative pole, so they will move until there is no more force on them. And that would be when they reach the plasma membrane and they're right up against it. Now the electric field will be right across the plasma membrane at each pole, and no electric field inside. So there's actually no way for the field to affect intracellular organelles under these circumstances. And here you can see on the right an image of the field lines penetrating just the plasma membrane but not inside the cell. However, this takes some time for the charges to rearrange, to move to the poles. And typically it's about a microsecond. So what would happen if we imposed an electric field that was so fast that it was faster than a microsecond before the charges had a chance to rearrange? And that's exactly what we're doing with our 100 nanosecond pulse. This is faster than charge redistribution time, so the electric field can penetrate into the cell interior as shown here and affect all the organelles, the nucleus, the ER, and the mitochondria. When you do that, you can have effects on cell functions such as secretion, protein targeting, and signaling pathways such as apoptosis. Now the main target for a nanopulse is the lipid membrane that surrounds all cells and organelles. And we've known for 40 years that you can put a voltage about 1 volt across a cell of 10 microns and cause pores to open up in the plasma membrane. And that means 1 volt across 10 microns, it's equal to about a kilovolt per centimeter. However, if you want to put pores in the organelle membranes, you'll note that they're much smaller, and the distance between the two membranes here is less than a micron. So for organelles, you need a volt per micron, or more like 10 kilovolts per centimeter. So that explains why we have to have such large fields across the cytoplasm, because if you want to permeabilize organelle membranes, you need 10 kilovolts per centimeter. So to summarize, a nanopulse electric signaling uses very short pulses, and we apply them to the cell. They permeabilize the plasma membrane, get into the cell because they're so large and so fast, they can permeabilize the internal membranes as well, and then leave the cell. And it's this very rapid change in voltage and high voltage field, high electric field, that allows us to have effects on mitochondria, nuclei, and endoplasmic reticulum. Other videos on the website will explain some of the targets, some of the effects that we can have on these cells, such as stimulating apoptosis and stimulating an immune response. as well as how we measure the permeability change using patch clamp, and exactly what the mechanism for the field to drive water pores into these membranes.